Curvilinear coordinate system 6. Perform the following line integrals along 1/4 of a unit radius circle traversed in a counterclockwise direction. The center of the circle is at the origin of a Cartesian coordinate system and the quarter circle of interest is in the first xy quadrant. The first integral is dr dot b, the second one is dr times the scalar function phi, and we have already done part A and B, so we will do part C, which is repeat parts A and B using a polar coordinate system. Okay, and this is the path we're going to consider. Now, when we go to polar coordinates, the transformation between Cartesian and polar coordinates is x is equal to r cosine theta and y is equal to r sine theta. And the position vector r, which is r hat in polar coordinates, is x hat plus y hat in Cartesian coordinates, which is r cosine theta hat plus r sine theta hat. And therefore, we can read the er hat unit vector here. It's cosine theta ex hat plus sine theta ey hat. But anyway, so if we take the derivative of the position vector with respect to r to obtain the scale factors, we would obtain cosine theta ex hat plus sine theta ey hat. So if we do it formally, we are going to obtain cosine theta ex hat plus sine theta ey hat. And this tells us that the unit vector on the radial axis is, because its magnitude is equal to 1, this divided by its magnitude, is cosine theta ex hat plus sine theta ey hat. Okay. And what about the e theta hat unit vector? Well, we can take a derivative of the position vector dr d theta, and this will give us, if we go back and take a derivative, minus r sine theta ex hat plus r cosine theta ey hat. Minus r sine theta ex hat plus r cosine theta ey hat. And we can determine the unit vector e theta hat that's the derivative of the position vector with respect to theta, angle theta with respect to theta, and then dividing it by the scale factor h theta, which is its magnitude. Now, what is the magnitude of this vector? You can see it's r. So this divided by r will give us minus sine theta ex hat plus cosine theta ey hat. Okay, so as a summary, we have the two unit vectors. Er hat is equal to cosine theta ex hat plus sine theta ey hat, and the other unit vector on the tangential axis is minus sine theta ex hat plus cosine theta ey hat. All right. And this will allow us to determine also Ex hat and Ey hat in terms of Er hat and E theta hat. Note that Ex hat is Ex hat dot product with E theta hat in E theta hat direction, and it's the dot product with Er hat in Er hat direction, and Ey hat is equal to Ey hat dot product with E theta hat in E theta hat direction, and Ey hat dot product with Er hat in Er hat direction. So I can write Ex hat is equal to, what's the dot product of Ex hat with Er hat? It's cosine theta, so it's going to be cosine theta Er hat. And what is the dot product of Ex hat with E theta hat? It's minus sine theta, so minus sine theta E theta hat. And similarly, I can do Ey hat in terms of the unit vectors in the polar coordinate system. Ey hat is Ey hat dot product with Er hat, which is sine theta, so it's sine theta Er hat. And cosine theta E theta hat. Okay, now we're ready to tackle the problem in part A. So let's call this part A prime. Our vector v is 2x Ex hat. So this written in polar coordinates, x is r cosine theta, so this is 2r cosine theta. Ex hat is cosine theta Er hat minus sine theta E theta hat. And on this path, r is equal to 1. So that's what I need to consider. So I can rewrite my vector v in polar coordinates as 2 cosine squared theta Er hat minus 2 cosine theta sine theta E theta hat. 2 sine theta cosine theta E theta hat. Okay, and next I have to write the position displacement vector. Differential displacement in polar coordinates is basically we have a displacement, an arc length of r d theta here. So this is in theta hat direction, remember. This is varying the angle theta in the counterclockwise sense. So this is going to be r d theta in E theta hat direction. R d theta in E theta hat direction. Well, r is equal to 1 on this path, so we have d theta in E theta hat direction. So that's what we have. Now we're ready to perform the integral. The line integral dr dot product with the vector b is the integral. Now we have dr vector in E theta hat direction. So Er hat dot E theta hat is 0, so this will not contribute. We will have minus 2 sine theta cosine theta d theta. So minus 2 sine theta cosine theta d theta. And how do I vary the angle? The angle theta goes from 0 to pi over 2. So the limits of the integration are 0 to pi over 2. And what is 2 sine theta cosine theta? This is minus integral from 0 to pi over 2. That's sine 2 theta. It's a half angle formula, d theta. And the integral of sine 2 theta is minus sine 2 theta is plus 1 over 2 cosine 2 theta, and that is to be evaluated between 0 and pi over 2. And when we substitute pi over 2 here, we will get cosine pi, which is minus 1. When we substitute 0 here, we're going to get 1. So this is going to be minus 1 minus 1 minus 2 divided by 2. So we can see that the integral, line integral, dr dot v will become 1 over 2 minus 1 minus 1 over 2, which is minus 2 over 2. So we find our answer, dr dot v integral is equal to minus 1, also using the polar coordinates. Now to double check what was the answer to part A, minus 1. So indeed this is the correct answer. Now we're going to do part B of the problem. Part B prime. Our scalar function phi is equal to 2x. This written in polar coordinates is 2r cosine theta, but r is equal to 1. Therefore, this is 2 cosine theta. So we substitute r is equal to 1. Now our line integral dr phi is going to be the integral. Again, we have r d theta as our, in e theta hat as our differential displacement vector, but r was 1, so remember we get d theta e theta hat. So therefore we have 2 cosine theta d theta in e theta hat direction. Again, the angle varies between 0 and pi over 2. But in this integral, I note that this unit vector e theta hat is position dependent. It varies with theta. So e theta hat varies with theta. So I have to be careful in performing this integral. Therefore, I have to write this as integral 0 to pi over 2 cosine theta. Then I have to substitute for e theta hat what I have found in terms of ex hat and ey hat. Minus sine theta ex hat plus cosine theta ey hat. Minus sine theta ex hat plus cosine theta ey hat. The stationary unit vectors are ex hat and ey hat, but e theta hat is theta dependent. Therefore, in this integral, I have to consider its theta dependence. This is d theta. Okay, so this is going to become integral from 0 to pi over 2. Now I have minus 2 sine theta cosine theta again, which is minus sine 2 theta d theta in ex hat direction. That's the first one. And the second one is 2 cosine square theta. So 2 cosine square theta d theta in ey hat direction. If I perform this integral, I'm going to obtain for this one cosine 2 theta over 2. So 1 over 2 cosine 2 theta evaluated between 0 and pi over 2 in Ex hat direction. And for the second part, integral from 0 to pi over 2, for 2 cosine square theta, I can substitute cosine 2 theta plus 1. This is 1 plus cosine 2 theta d theta in Ey hat direction. The first one gives me 1 over 2 cosine pi is minus 1 and cosine 0 is 1, so minus 1 in Ex hat direction. The second one gives me integral of d theta, that's theta, and then I have the integral of cosine 2 theta d theta, that's 1 over 2 sine 2 theta. And this will be evaluated between 0 and pi over 2 in Ey hat direction. And as you can see, when you substitute pi over 2, here you will have sine pi and sine 0. They're both equal to 0. So this part gives me no contribution. So this is just 0. But I have the theta here, which is going to give me pi over 2 to 0, pi over 2. So my final answer for this line integral dr scalar function phi is minus Ex hat plus pi over 2 Ey hat. And I can check this answer with what I have found previously for part B, minus Ex hat plus pi over 2 Ey hat. That's correct. And if you wish, you could convert this to also polar coordinates by substituting Ex hat is equal to cosine theta Er hat minus sine theta E theta hat, and Ey hat is equal to sine theta Er hat plus cosine theta E theta hat. So let's also do that. So this is equal to minus Ex hat, which is minus cosine theta Er hat and plus sine theta E theta hat. And then we have pi over 2 Ey hat, which is plus pi over 2 sine theta Er hat and then we have pi over 2 cosine theta E theta hat plus pi over 2 cosine theta E theta hat. So let's just clean this up. We have pi over 2 sine theta minus cosine theta Er hat. So let's put it together. Pi over 2 sine theta minus cosine theta Er hat. And then we have sine theta E theta hat and pi over 2 cosine theta. So we have plus pi over 2 cosine theta plus sine theta E theta hat. Okay. So we can also write it explicitly in terms of polar coordinates. Okay, so in this exercise we have solved the two line integrals using polar coordinates. First, I've started out by noting the transformation between Cartesian and polar coordinates. I have determined the unit vectors by taking a derivative of the position vector with respect to r and theta and dividing it by the magnitudes. I have found these two unit vectors here, er hat and e theta hat. And then I was able to write ex hat and ey hat in terms of er hat and e theta hat, noting that the ex hat component on e theta hat is the dot product with e theta hat, and component on er hat is the dot product with er hat. And similarly for ey hat, I was able to determine these unit vectors. Then I have written the vector v 2x ex hat as 2r cosine theta. For ex hat, I have substituted this result, and then I noted that r is equal to 1 on this contour, and taking the dot product with the r vector here, the r vector is r d theta e theta hat, which is, since r is equal to 1, d theta e theta hat gives me minus 2 sine theta cosine theta d theta. Then noting that going from the x-axis to y-axis in the counterclockwise sense, I changed the angle 0 to pi over 2, and 2 sine theta cosine theta is sine 2 theta. I can take the integral, gives me 1 over 2 cosine 2 theta, evaluated between 0 and pi over 2, which is minus 1. For part B, I have written the scalar function 2x as 2 cosine theta with noting r is equal to 1. And for dr vector, I have a d theta e theta hat, but this is an integral over theta. E theta hat varies with theta. So I had to substitute for e theta hat what I have found in terms of Cartesian unit vectors, minus sine theta ex hat plus cosine theta ey hat. And then I performed the integral, noting that sine theta cosine theta is 2 sine theta cosine theta is sine 2 theta, and 2 cosine squared theta is 1 plus cosine 2 theta. And performing the integral, I found the answer identical to part B. And I finally noted that I can write ex hat and ey hat in terms of the polar unit vectors, er hat and e theta hat, to give all the answer in polar coordinates.